I took it to 2 decimal places, exactly. And the reason I like you doing it as a decimal is because if you do it as a decimal, you end up with an easier to understand number. Like 6 over 325 is a little bit challenging mentally to kind of figure out. You have to kind of find common factors. Daniel, what's on your mind? Ask me that question.
I'm just trying to see.
Oh, let me make it bigger. Let me make it bigger. I'm sorry.
Total number was 325.
That's what I was told, right? Here's the sum. I double checked it with the sum command here.
But there were 20 of us, so shouldn't it be...
What did I say about my counting skills? Don't forget, brother, I can't count more than Dan. So here's what, so I love the fact that what Crystal said, she's like, it's parabolic. And you know, it's arguably parabolic. It is. It's arguably parabolic. I mean, what the hell? Hey guys, remember your last out of class exam? Let's throw it on there. Polynomial, power 2. There. That's not bad. That's not bad. It's definitely not linear. I mean, we can put a linear fit on there.
What the hell? Why not?
Why not? Well, the trick with that is, and go something. The trick with doing any of that, with trying to guess at what trend line should fit, is that we still have a lot of noise in our patterns here with these dice. Yes, we still got a lot of noise. So how can we minimize the noise in our dice? Roll them more. Roll them against the carpet. Roll them more. So I kind of predicted you would say that. I kind of did.
He can read you.
I can read
like
you.
an open book.
No, like a book. Like a wonderful, wonderful book. Lessons. Let me throw this in intro. I'm probably going to save this spreadsheet so we can use it next time. Experimental 2 dice. So, let me shut this bad boy down. And let me open up roll 2 dice. So, check this out. See if you understand what's going on here. What I've got, it's something similar to what we did last time. So you've got 2 dice. It's just like the pie chart, and you're going to see 2 pie charts at the bottom. Die number 1, die number 2. Die number 1, die number 2. Both those pie charts. They are going to behave just like the ones yesterday as we roll more and more and more dice. So what you'll see as we hold down that F9 button again is you're going to see those things start to pizza pie out into, here, I'll show you the first 6. Let's roll 6 times. 1, 2, oops. Hang on, time out, 1 second. I gotta change this to circular. Formulas, iterative, done. There we go. 2, 3, 4, 5, 6. So there's 6 rolls. Now what's interesting is, we ended up with the same outcomes on both the dice. Now that doesn't mean they're rolling the same things the entire time. As you can see, one die rolled a 1, one die rolled a 6. But we definitely did not get one of each number like we analyzed before. Remember that? The whole, it's really hard to get 1, 2, 3, 4, 5, or 6, or even all the numbers 1.5% of the time, as Joe said, within 6. So here's within 7, boom. There's within 7, you can see what just happened there. We picked up a 5 over here, but we picked up another, looks like another 1 over here. Yeah, another 1 right there. So what I'm going to do is, I want you guys to watch this guy right here, and see how if he looks like the curve we just got. Remember that curve we just got? It kind of went up and then it spiked and then it dropped off and leveled and dropped again. Let's see if we can make this. Now I'm going to go 325 rolls. Let me get my stapler. We're going to go 325 rolls to mimic exactly what you guys did with your rolls. Okay, or at least what I counted anyway. So here we go.
Evolution again.
It's evolution. It's like watching evolution. Such a great quote. Wait, getting close. There's 325.
That 9 was just going up during the last few parts.
What was going up? The 9?
The 9.
I wasn't even watching. I was watching the damn buttons on the keyboard. So Nick, we had a gap at 9 and it kind of filled.
Only the 9 was just going up.
Only the 9. So die. This goes back to what you were saying about you had it 6.
Right.
This one had it with 9. So it was short on 9s. But then what happened? It caught up. Now the question is, what does it catch up to? That's what we're getting at here. That's what we're getting at here. Because if I made you guys run this experiment again, which I won't do because it's tedious, but if I made you guys run this experiment again, do you think you're going to get these values again? No.
They would be similar.
They'd be similar but not the same. And that's similar but not the same. This is the idea I just had when you guys were rolling the dice. We need to talk about what's called a margin of error. The offness of the true value from the value you're getting. The percent error, if you will. The percent error of the true value from what you're getting should shrink as the number of trials goes on and on. So let's let this thing keep going. Look down here. How about these? How are these looking down here?
Starting to pie out.
Looking pretty good. Starting to pie out. All right, here we go. go. Let's get the stapler on there, let it do its magic, and watch what happens.
Do you need more space on it?
I want to watch some evolution too. What's happening? And you'll notice it corrects itself every once in a while because it has to rescale because of the new values. So we're about 1,000 trials. Give me some observations. It looks more parabolic now, doesn't it, Crystal?
Yes.
So her parabola idea is starting to look a little bit more, but I also noticed that 7 spike was up at 19%. It just dropped to 18, and the other ones are starting to creep up to it. That's interesting to me.
So the odds of rolling a 7 and crapping out are really up there.
Yeah, I'm not feeling enough.
But you're sick.
But this is more interesting. Evolution is more interesting than some goofy Italian guy with a big nose. What is happening, friends?
The middle is remaining up top.
Say that again, Nick.
The middle, the 7, it's still the highest.
The 7 is still the highest.
This gap is smaller.
But the gap between 7 and the rest are small. Good, Andrew. Give me some other observations. I love this. Give me some more.
Well, there's
Still looks like a parabola.
It's still looking parabolic. I like that. When you say parabolic, what features of the parabola are you seeing, Crystal?
Increases and then decreases.
Uh-huh. And how does it increase versus decrease, Jordan? I'm sorry. I saw your hand move. It looked like you were drawing it for me.
I did.
Yes. You use one word that wraps that up.
A curve.
Say that again.
A curve.
Oh, that wraps this idea up.
Oh, I don't know.
It's symmetric.
That's what I'm looking for. It's your symmetry, right? I can tell what your hand was showing me, Jordan, because you were going up and then back down in the same way. So it looks to me like the left side of the curve and the right side of the curve are just about the same, yeah?
Increasing at an increasing rate and then it hits its high
We
point.
got it increasing, then it hits a high point, Crystal.
And then decreasing.
Oh, that's genius. I love it. Good. Well, that would mean that the probability of a 2 is the same as the probability of a 12. Huh. Look at your dice.
They're almost
Do you
exactly.
believe that?
Yes.
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 We're gonna let this roll for a while. I want to come back to it. What I want to do is I want to come over here. And I want to see if we couldn't have figured this out without having you guys roll 325 times. I'm arguing at this point that we could get these numbers without having to do all that rolling. And therefore we can analyze craps more efficiently than actually have you guys lose a bunch of money to figure out what the die rolls are. Because the only way to figure this out is either 1, theoretically, or 2, analytically, which is what we're doing right now. But think about it. You'd have to play craps 325 times to get this data, which will cost you at least $325, if not much, much, much more. Of course, you might win it sometimes too, which we have to factor that in, but probability says you won't. So, let's figure it out. Let's go back to the outcomes. Which are still 2, 3, 4, 5, 6, 7, 8, all the way down. Yes, all the way down. Let's try to jump right to the probability column. Which is going to be, how many ways can we get that over how many ways can we roll the dice? That's the first thing we have to figure out, I think. Probability.
It's like a delta in the middle of it all.
Say that
It's
again?
like a delta in the middle of it all.
Look at your dice.
From lighting.
Look at your dice. I'm making up words. If I was to throw those 2 dice, how many different ways could they come up?
36.
A vote for 36. You actually had to answer this question in your last project, didn't you? It was either one of the ones you turned in or it was one of the examples. I forget which. But one of them was roll a die 2 times. How many outcomes are there?
36.
They're 36 because it's 6 times 6. Yes, exactly. This is the basis, FYI. This is the basis of why your passwords keep getting longer for all your secure accounts. Back in the day, when I had a Hotmail account originally, 4 characters, 4 numbers was the password. That was it. 4 numbers. That was it. That's all they required. 4 numbers. 4 numbers for a password. It would take a supercomputer less than 1/1,000,000th of 1 second to crack that nowadays, because there are only 10,000 possibilities. There are 9 digits, yeah, 0 through 9. So there are 10 digits, 0 through 9. So each of the numbers is like rolling a 10-sided die. So 10 times 10 times 10 times 10 is 10,000. A supercomputer just rolls the dice really quickly. It starts at 0, 0, 0, 0, and then tries them all till it hits it. Less than a second, your password's cracked. How how many people in here have a 4-digit password anymore? Nobody does. Except for your phone. Your little phone probably has one of those, yeah? Now, here's a question about iPhones, and I don't know the answer to this, and I think we may have answered this before. Does an iPhone lock you out after a certain number of tries if you try again? It does. So you can't, say that again?
Yeah.
It does. So you can't just keep trying from 0, 0, 0, 0 until you get to 1 because it's going to lock you out eventually. But the thing about other passwords is depending on the encryption, sometimes you can. Your password for school for your network account has to be between 6 and 15 characters, case sensitive, numbers included. That's with caps, case sensitive, caps or lowercase.
Oh, okay.
That's 52. Plus 10 digits is 62 possibilities for each character. So if you have a 6-digit number or a 6-character password, it's 62 times 62 times 62 times 62 times 62 times 62. That's big. That's big. But then you also have 62 to the 7th, 62 to the 8th, up to 62 to the 15th. If a computer tried to brute force your password, assuming it didn't get locked out, it would take it a maximum of 1,000 years. Even testing 10 billion numbers per second, it would take 1,000 years for it to crack your code. At worst, at worst. It would probably take it somewhere around half.
Someone who knows you has a better chance than a supercomputer.
Yes, because
they
supercomputer doesn't know
what you
anything.
know.
Yes,
Right.
now, if you've trained it to look for code, like it might know your birthday, or
Right.
your address,
Or your favorite hot spring.
something like that, and it might try those first. But
Are you telling us
if
your
it's
password,
trying,
your favorite
she
hot
is.
spring?
She just did.
Yeah.
Done.
Yep.
Yeah, done.
What was your email?
So, but the point is, it all ties back to Nix 36. All of it ties back to Nix 36. We spent quite a bit of time in 243 talking about that too.
Girl 84.
What?
That was kind of creepy. I don't know why. That was kind
Hang
of
on,
creepy.
hang on.
We're back to 36 now. So you have 36 outcomes for your dice. Yes.
Yeah.
How many are snake eyes?
There's only two.
There's two ones, but there's only one outcome.
One
Yes.
possibility.
So if you hold those 2 dice in front of you, there's only one snake eyes.
Right.
You have to roll one on one die and one on. That's one outcome.
That's one.
So the chance of snake eyes is 1 in 36. Friends, as a decimal, if I can do this in my head really quickly, that's about 3%.
Well, considering the data's up there.
No. I mean, actually, that's about 1 in 33. That's about 1 in 30. No, I'm approximating. Pretty close. It's 1 in 33, which would be 3%. So we call it. Sit down a little late. All right. Now, let's go down to 3s. Everybody take your dice. Make a sum of 3. Okay? Just make it put it on your desk, like sitting up at a sum of 3.
No subtraction.
No subtraction, just addition. Yes. Oh, that's a good problem. If you subtract the pips, ooh, you might have just made up your take-home problem.
Oh, come on.
That's a good one. That's a dip or a multiplier. Multiplier might be better.
I play a game called Zombie, or it's called Last Night on Earth. And part of the idea is to get zombies on the board. And you have to roll first to see whether or not you get zombies, and then you roll to see how many zombies you can get. Okay?
When did this zombie thing come back?
I don't know, but it's big.
understand the zombie thing.
My son's
Okay,
playing zombie.
so what we did is we made a house rule that if you roll a 1 or a 2, either into bring zombies on or how many zombies you get on, you get a reroll. One
So
reroll.
confused right now.
Well, the thing is, you need to get zombies on the board. You
Yes.
roll a 1 or 2, you just don't.
Yes.
So we made a rule to increase your odds of
So,
getting something higher.
You're telling
than
us
1 or
why.
2.
You're actually describing why you're not getting them on the board right now, yeah?
Right.
Because you guys have a 3 on you. You got a 3 in front of you?
Yeah.
Get a different 3 in front of you.
Well, just switch the dice around.
Good.
There really is no way.
There is, isn't there? That's why I said grab 2 different color dice. So somebody like Nick has a blue and a red die. One way to make a 3 is have a blue 2 and a red 1. Another way to make a 3 would have a blue 1 and a red 2. That's a different sum. Those are different faces. If you're turning the dice, you're making a different outcome. Yes? Does that make sense? Is that fair?
Yeah.
So there's.
Good. Make 3 a different way.
Can't.
You can't. You're done at 2. So it's 2 in 36, which should come out about 6%. About twice as likely. Look at that. It hasn't moved a while because it's stabilized. It's actually moving quite a bit. It's just that we've gotten so close to the true values, there's no reason for it to move anymore. This should round up to 17 as we let time go on, but that's more time. How about 4? Make 4 with your dice. A sum of 4. Very nice. Once you've done it once, make a sum of 4 again. Ryan's gonna do it by roll. That's awesome. Just keep rolling until you get it. That's a good math question. How many times did you have to roll until you saw each way of 4 fall at least once? I don't know how to answer that question. That's a great question.
That's my problem.
That's a fantastic question.
Yeah, there's 3 ways.
How many times would you have to roll a pair of dice until you averaged seeing every multiple of 4, or every sum of 4 at least once?
Well,
I have to do 1 minus the chance of not ever seeing them and get that down. We'll come back to that. Okay, so you made 4 twice now?
3 times.
You made it 3, Nick's made it 3 times, you guys made 4 3 times? Can you make it a 4th way?
Nope.
No, because you either go 3 or 1, 1 or 3, or 2 and 2. Now, why am I not counting 2 and 2 twice?
Yes.
Yes! So you're upset with that, Shelley. Why are we not counting 2 and 2 twice? Everybody put your dice down.
You only have one.
Everybody put your dice down. I think we can explain this via the dice. Make 3 and 1 on your dice. 3 and 1.
Now switch and do this.
Now find 3 and 1 a different way.
Right.
So you have to turn the dice to do that. Yes, you're actually using different faces. Everyone with me so far? So 3 and 1 and 1 and 3 are different. Okay, everybody, go 2 and 2.
You can't do it.
Now do 2 and 2 a different way. And you can't because you don't actually turn it's the same 2 faces. Shelley, very, very good. That's why in craps, when you bet on for the hard way, this is for the hard way, double 2s. Because it's twice as hard to get 4 this way as it is to get 4 in any of the other combinations of 1 and 3, 3 and 1. Does that make sense, Shell? Thank you. Go, Nick.
What about switching the colors from left to right? Would that count?
No, that's a good question. It's still the same faces, though. You have to ask, are you turning the faces? If you go like that, you are switching the dice around, but you're not talking about the sums of the faces anymore. You're talking about the spatial position of the dice, which is a cool math problem in itself. But it's not the one we're talking about.
Alright.
Now that, if you're following the pattern, you'd think it should go to 9%.
Yeah, it's 8.
But it's 8.125. 336 is 1/12, which is just over 8%. Which means these guys this is rounded down, that's rounded down, and that's rounded down as well. So we're estimating. Okay, good. Make 5 as many ways as you can.
There's 4 ways.
That was great.
There's 4 ways. It's going up.
A vote for 4. Nick is saying it's going up by 1 each time. That's clever. Ron, what you got?
I was
Oh, gotcha.
agreeing with that.
So Ryan's agreeing with Nick. Nick says there's 4 ways. 1 and 4. Yeah, 1 and 4, 4 and 1,
3 and 2.
3 and 2, 2 and 3. You can't make doubles with 5, right? You can't do doubles with these numbers. Good. So this is going to be 4 and 36, right? That ends up being a 9th, which is about 11%.
Yes.
Which is agreed. If you look at, and Andrew noticed this, he said, this hasn't moved in a while. And what he's saying is, these graphs haven't changed very much. But they're just changing so imperceptibly tinily that you're not noticing it. They are changing if you look in here.
Well, yeah.
Those are changing, but to these decimals, now watch. Let me swing the camera around too so you can see it. There is change going on. It's just happening back so far in the decimals that I have it rounded down. So let me scroll in here. We'll go back to our chart in a second. Bump that P of X column out. There you go. Oops. Stick removed. There we go.
User error.
Well, exactly. It usually is. So there is definitely change going on, but to 2 decimals there is not change going on. And even if I was to graph, you're actually graphing all these full values, but you see how they're stabilizing. I mentioned this yesterday, and Nick asked a great question. I think it was Nick or it was Joe. One of you guys asked a question about how long would you have to wait until each decimal point stabilizes?
Yeah.
And my quick and easy answer is 10 times more for each decimal place, because you're getting 1/10 more precision, or 10 times more precision each time.
Stop.
Must have fallen off again. Yep, it did. I just broke my old swing line. I had this great swing line stapler for years. Big cast iron thing. And it was great for holding down the F9, but it's this cheap plastic piece of crap now that does that constantly. So if it stops again, let me know and I'll swing it back and I'll fix it again. Ah, the olden days of swing line cast iron staplers. Those were the days. Riding bikes without helmets.
Playing in the creek.
Playing in the creek, drinking the water. Not washing your hands. What are we up to? We're at 5. This is even a little. We're at 6. Try to predict what 6 is going to be.
5.
There should be 5 outcomes. Let's see if you can do it without using the dice.
Yes. So 5 and 1.
5 and 1,
1 and 5.
1 and 5, 2 and 4, 4 and 3,
3 and 3.
6 the hard way, 3 and 3. There we go. 5 and 36, which ends up being about 14%. Yeah? Ish. Ish.
Now it's going up by 3%.
Well, ish. It's going up. It's going up ish. What fraction is it going up by each time? It's about 3%. It's just shy. It's 1 in 36. We're adding 1/36 more each time. Each outcome, every single outcome, whatever the dice are sitting on your desk right now is an outcome. So Dave's sitting on a 4 and a 1. Green 4, white 1. Rye's got a 4 and a 2. Red 4, blue 2. Nick's got a 5 and a 1. Blue 5, white 1. Chris has a 5 and a 1 as well. It's all the same sum. That's kind of wild. But every one of those outcomes is 1/36 likely. If I say, what's the chance of rolling a white 1 and a blue 6? You say it's 1 in 36. That's a different question than what's the chance of rolling 7? Because there's different ways to roll a 7, but there's only one way.
You finally hit 17.
Oh, there we go. And it had to. It had to eventually. But you're about to see why. You're about to see why. What's the chance of rolling 7? Which is my question. It's 6 in 36. Count them all up and you'll see. 6, 1, 1, 6. 4, 3, 3, 4.
Round up.
5, 2, 2, 5. It's 1 in 6. It's 1 in 6, which ends up being about 17%. So rolling 7 is just like rolling any single number on a single die. Yes!
Parabola.
So it's actually not parabolic though. That's what's so cool about this. It's not a parabola. It's an absolute value function, which is one of the rare ones you ever see in statistics. It's actually a perfect 90-degree angle. It goes up, hits a sharp point, and drops back off again. That's it. It's one of the few that does that in statistics. It's perfectly linear, followed by perfectly linear. It's got a great equation to make 243 analyze. And then notice what Jordan and Crystal said earlier was that it looks like 8 and 6 are symmetric as far as their likelihoods. Well, think about why. There were 5 ways to get 6, yeah? There are also 5 ways to get 8. Figure them out.
5, 3.
5 and 3, 3 and 5. 4 and 4, 8 the hard way.
6
and 2.
6 and 2, 2 and 6. If we had 7-sided dice, yes.
Well, yeah.
But there we go. There we go. Because what you want to do is you want to keep going up, but you have to have 4-sided dice than that.
Yeah.
So either 4 and 4, 2 and 6, 6 and 2, 3 and 5, 5 and 3. So yeah, indeed, it does start going back down again. 14%, which means there should be 4 ways to make a 9.
Yep.
And there are.
6 and 3, 2 and 6.
Yep, 6, 3, 3, 6, 4, 4, 4, 5. There's your 11%. 10 should match 4. 4 and 6, 6 and 4. 5 the hard way, or 10 the hard way, 5 and 5. So there's your 8%. And then we go down to 11.
6, 5, 5, 6.
6, 5, 5, 6 is all you can do, yeah? Same as 1, 2, 2, 1. Well, I say it's the same. It's the same likelihood-wise. It's a different sum, obviously, and they mean very different things if you're playing craps. 2 and 36, well, that's 3. 2 and 36, which ends up being your 6%, I think it rounds to, yeah?
There's only one way to get a 12.
And there's only one way to get boxcars, and there's only one way to get snake eyes. 1 in 36, which ends up with 3%. And what's cool about that is, if you sum up all those fractions, you get 100%.
You should.
1 plus 2 plus 3 plus 4 plus 5, that's 15. 1 plus 2 plus 3 plus 4, that's 15. 15 plus 15 is 30.
Plus 6.
Plus the 6 in the middle is 36. Over 36 is 100%, which that's as well. Done. Done. That's the distribution. That's the craps distribution. That's the craps distribution. The most common roll? 7. Fortunately, when you play craps, they give you not only 7, but also 11. So if you throw the craps dice, and you roll a 7 or an 11, you win. I think it's 2-to-1 payouts. Something like that.
It is 10 out of 36.
What is the chance? That's my next question is, what is the chance that you throw 7 or 11 on the first roll of craps dice? Everybody do it. Let's do it experimentally first. Everybody, right now, there's how many of us out there get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17. I can't divide by 17, that's okay. We'll do it anyway. Everybody, here we go. Big money, babies, big monies. Roll them. All right, 17 people. How many of the 17 got 7 or 11 on this first roll? Oh, goodness, 1. Excellent. Hang on. Let's keep a running total of this. We got 1 and 17. Don't tell Julie Keener we're doing this, just so you know. Do it again. She'll kill me if she finds out I did this. All right, wrong again. That's okay. Count it, hits the ground and face up, Joe. You can count it. 7 or 11 this time. Jordan's on fire. 1, 2, 3, and 17. Do it again. We're gonna add fractions completely. I'm sorry, Joe, if you're watching this. Please don't kill me. You know where I live. 7 or 11s.
Hey.
Jordan's on fire. What is that again? Check the dice. This is where the pit boss goes and stands
There
next
you
to
go.
you.
She probably has
This
to
is where the pit
double.
boss goes and stands next to you. Okay. Do it again. Do it again. 7 or 11.
Sorry.
Well, phew. You can stay at the casino. 3 and 17. Do it again.
All my fight money.
It's all my fucking money.
I'm putting my money in her.
7 or 11.
Oh, 11.
4, 5, 5 and 17.
Oh, I got it.
6 and 17. Do it again. How we doing? How we doing? Thank you. Listen to the table, man. 7 or 11.
I like to bounce.
4 and 17. Do it again. It'll be fun. It'll be fun to track not only who gets, not how many 7s, 11s, but where they show up in the room. Because it's fun watching the patterns pop up. Like that time it was 3 and 1 over here. Jordan was boom, boom, boom right at the beginning. And see if that spreads out over time. 7 or 11 this time. And see, it's kind of spreading out. 1, 2, 3, 4, 5. Let's do one more. Actually, let's do 3 or 4 more. 7 or 11, just to make the math easier for me. 1, 2. Yeah. Oh hell, let's do one more. Let's get a computer with these for math work. That is a 5. Whoever's that was, it's a 5. It's over here.
Here, I got 11.
You got 11. Okay, so 7 or 11. We got Chris and 1, 2, 3, 4, 5, 6, 7. All right, let's add up. This is why I'm apologizing to Julie. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh hell, do it one more time. Let's make it easy. 17 times 10 is easier than 17
Did you
times
not want
9.
to get lean class?
What's that?
Did you not want to get lean class?
Well, no, because we're going to add fractions the wrong way. And you're going to forget that I did this right after I do it. 7 or 11? 1, 2, 3, 4, 5. Okay. That's 17. If I add up all these tops and bottoms, I get 117 total trials. Or 170 total trials, because 17 times 10, yeah? Count how many times we've won. 4, 5, 8, 14, 18, 20, 37.
How's that bad? Shooting it like one big trout.
It's because you don't add fractions that way.
What?
Because you keep it coming. Never mind, don't worry about it. You are treating like one big trial. That's exactly right. So what's 37 out of 170?
22%.
22%. Now, could we have figured out it was 22% without making you guys lose a bunch of money in the process? Because inevitably you would have had to have lost a bunch of money to get to that value.
Just add the percentage.
What percentages?
The likelihood of the 7 and 1.
Did you hear what Andy just said? I don't think he did over here because he's speaking very quietly. When you hear the word or in probability, it means to add events that can't happen at the same time. So for example, if you throw 2 dice, like you just did, you can't get a 7 and an 11 at the same time. There's a fancy word for that called disjoint. They're disjoint or mutually exclusive. If one thing happens, the other one can't happen. So if you want to figure out what's the chance of rolling 7 or 11, all you've got to do is add up the chances of 7 with the chances of 11. They add together and they become larger. Hopefully it makes sense. They should get larger, yes?
8 divided by 36.
So it should be 8 divided by 36, because you have 6 in 36, or roughly 17% chance of rolling a 7. And you also have 2 in 36, or roughly 6% chance of rolling an 11. So the probability of rolling a 7 or an 11 should be 8 in 36. Without the rounding error, what does 8 in 36 round to?
Point two 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 two.
Which means we just observed the exact percentage we should have observed, but we knew it going in versus having to lose at least 170 bucks or bet 170 bucks in the process. This is where you have a house edge going into the games. Go in. I'm not saying not to gamble. That's not what I'm telling you. I'm not saying not to gamble. I'm telling you to gamble smart. Don't gamble like I walk. Gamble with the knowledge, first of all, that you're going to walk out with less money than you walked in with, on average. That's why Vegas keeps its lights on all the time. I can afford to. There's a great cartoon. Did I share it with you, the cartoon? There's a picture. You know there's a sign when you go in on the strip on Vegas that says, "Welcome to beautiful Las Vegas." Big sign, lights, and arrow. Well, Fabulous Las Vegas, I think you're right, Fabulous Las Vegas. Somebody did a funny little cartoon of that where they put that sign on the bottom, a small sign tacked on, generously paid for by people who are bad at math. Because that's the idea. People think, if I just keep playing, I'm going to win. Guess what? If you just keep playing, you're going to lose. That's the point. Every game in Vegas is rigged against you. The people that win are the ones that stop. That's the whole point. The movie Casino, De Niro, Sharon Stone, years ago now, it's probably 20 years old at least now. There's a scene I'm going to paraphrase. I'm going to paraphrase because I can't remember it exactly. There's a bunch of Japanese businessmen at De Niro's casino, and they're playing poker, or they're playing something, poker or blackjack, I can't remember exactly what, some game of, roughly game of chance, and they're crushing it, and they're smart, so they decide to leave. They gather their chips, and De Niro sees them try to leave, and he calls down the front desk, and he goes, shh, 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 shh. And they try to check out, and the front desk clerk says, gentlemen, your flight has been canceled. We can't get you to the airplane needs to be, we'll get you on the first flight out in the morning. And they're all pissed because they want to go home. Right? You know, they have a great vacation, they want to go home. And they said, please, have the best suite in the hotel on us. And tell you what, here's some more chips. Go gamble some more while you're here for the night. What do? Gamble all their chips away, plus the profits they made the first time. Because as long as you keep them playing, these are going to kick in. Remember how noisy our graph was originally? We had too many 6s and 7s on our graph. Do you remember that? Let's take a look at it again. You might not. I do, vividly. Let's swing this up again. There's our perfect graph. We'll come back to him. Let's go back to our imperfect graph. And I only say that because, where the hell did it go? Experimental, what did I call it? Here it is. There. We had too many 7s. We were operating at above an 18% of 7s. We also had too many 6s. 6s should be showing up around 14% of the time. We're above 16% of the time. Which means we were underestimated somewhere else in here-ish. But that's not going to happen in the long run unless the dice are rigged. But guess what? The dice are never rigged in Vegas because what do they do constantly? They replace them. How many of you guys have seen decks of cards and dice from Vegas that have been retired? They drill holes through them and they throw them away, I believe. Those are cards that are deemed not random enough anymore, and dice that are deemed not random enough anymore. Because every game in Vegas is based around this graph for 2 dice. That graph generates all the craps games and all the dice games. That's it. But you don't get it when you only observe a couple hundred trials. You get the noise within the graph. You only see the true graph either number 1 with infinitely many trials. We're up to almost 50,000 trials now. Pretty rad, huh? Pretty rad. And look how stable the first couple decimal points. The 0.027, I believe, is the first 3 decimals of 1/36. I believe it is 0.027. 0.029, so we're still a little bit high down here. We're still a little bit high on the 12s. But guess what happens if we let this run all night? They stabilize this. And I wish I could. This is the problem I have in my own classroom. I used to teach high school, it was great. I could put the stable on thing, let it run all night. Come back in the next day, perfect triangle. Things are off by maybe 1 or 2 in 100,000 trials. Amazing stuff, amazing stuff. I get booted out here. It's all good. You guys get the point. So, let's do one more probability and then kick you out of here. So have a nice Thanksgiving. Because I want to set the stage for craps for Monday. I want to have you guys playing craps on Monday. We can't gamble. I have Starburst. Hell yeah, I have Starburst. We can gamble with Starburst. I give you guys a bunch of Starburst to gamble with. This is perfect. This is perfect. I'll make it a quiz too. I'll make it in-class quiz. Oh, this is getting better. Betting with Starburst. Oh.
We call squeezing the pot.
Yeah. Very good, very good. Okay, so we know the chance of winning on the first roll of craps is about 22%. That still sucks though, right? That sucks. I mean, that's not very good. That means you're going to lose 78% of the time. So roughly, every time, well, I should take that back. You win 22% of the time, which is out of every 9 trials, out of every time you walk up to the table and throw the dice, 2 times out of the 9 on average, you're going to hit 7 or 11. Which, Jordan, you actually demonstrated that pretty well. You hit 3 and 10, if I remember correctly, I believe. So she was damn close to that. How many of you guys got 2 or 3 and 10? A couple of, Madison, your hand up a couple times, yeah? You had 4 and 10, you were a little bit above. Did anybody not hit 7 out of 11 at all in that experiment right there? Shelly, I'm going to give 2 of Jordan's to you and call you 2 and 10 and call her 2 and 10. Madison, you hit 3? 2. You hit 2, you keep your 2. Anybody else have 3 or 4 hits? Mike, I'm going to donate 2 of yours to somebody else, and on average, it ends up being about 2 and 9, right? About 2 and 9. But you can also lose. Oh, Mike, see, stupid snake. I think you guys get the point, yes?
Right.
I think we can take the turn on that. Now let's talk about the chance of losing, crapping out on the first roll. Crapping out on the first roll. You crap out when you roll a 2, 3, or 12. Snake eyes is a crap out, but you also crap out if you roll a 3 or 12. So, what's the chance of that? You always hear about snake eyes, of course.
3 and 36.
What's the chance of rolling a 2, a 3, or a 12?
4 and 36.
I hear it over 4 and 36. Think about why. We need this over here to answer that. I should add more sound effects to this.
So 11% chance.
So, there's about a 3% chance of rolling boxcars, about a 3% chance of rolling snake eyes. That's about 6. It's closer to 5.5 if you don't round off the rounding errors. Plus, you got about a 6% chance down here. So it ends up being 4 and 36 altogether. So the chance of 7 or 11 is 8 and 36. The chance of crapping out on the first roll is 4 and 36, which ends up being 1 and 9, which is just about 11%. So you're twice as likely to win on the first roll as you are to lose on the first roll. Genius. Isn't that genius? Why is that genius?
It keeps you going.
Because it keeps people at the table. If everybody's losing, I mean, the game could be totally different. It could have like very few ways to win, but when you do win, it's a huge payout. But that's stupid. That's stupid because people don't want to lose money constantly. It's a genius game because it sucks people in. 2 out of 3 of the probabilities that win or lose on the first win. It's 22 to 11. The odds of winning on the first roll are twice as good as the odds of losing on the first roll. Genius! Genius!
Is that basically the method that they use in the movie 21? They count cards and...
No, that's something totally different. We'll come back to that. That's a fantastic... And the book, Bring It Down the House, if you get a chance to read that, it's fantastic. Micah?
Can you back up? I'm not seeing what.
Oh, sure. There are 2 3s,
Okay.
1 snake eyes, and 1 12. So there's 4 total outcomes that are going to get you to lose.
So, but if you count it by percentage, would it be the percentage out of
It
100?
is, but remember these are rounded off. So if you go 3 plus 6 plus 3, it's 12, but this actually is closer to 11% without the rounding error.
Got it.
That's why I keep saying 11 out of 12. If these are all truncated down, and you can see it up here better. Okay, 2.7%, 2.9% is roughly, what is that, 5.6, plus 5.3 is 10.9, which is closer to 11. So that's what we're, it's a rounding error of 2 decimals is all. Fair enough?
Yeah.
Okay, so that's what makes the game awesome because it hooks you in. You want to keep playing because people are winning. People win 22% of the time. They win on the first roll. And have you ever seen a craps table? There's tons of people around it yelling and drinking and being lascivious. And they're giving them more free drinks. And they just keep being lascivious. And they keep playing because 2 and 9 people are winning. And then more are winning as we play. We'll save the rules of craps for Monday, yeah? Because they're pretty complex. Once you can get past the first roll, because we've only talked about winning and losing on the first roll, yes? 7 or 11 you win, 2, 3, and 12 you lose. That's only 5 sums, yeah? Aren't there 6 more sums to talk about?
Yeah.
We have to talk about what to do with those. But let's do that on Monday. Let's do that on Monday. Get you out of here. Go have a good Thanksgiving. Do this for me too. Try the homework for probability. You know what? No, we'll do that for Wednesday. Don't do that. Just take a weekend off. Just relax. Just relax. We'll do the homework on Wednesday. That's a good place. What's that, Jordan?
So yours says we.
Well, I mean, it's a long weekend. We'll come back and play craps.